Consider just a graph of y equals 1 over x. We need to include the negative 1/2 and 1/2 points. We need to include these points on every table for the basic graphs, except for the 2 to the x graph. So, how do we calculate 1 over x when x is negative 1/2? Well, means we're going to calculate 1 over negative 1/2. That means 1 divided by negative 1/2. So we get 1 times negative 2 over 1. Dividing by negative 1/2 is the same as multiplying by the reciprocal. And 1 times negative 2 over 1 is negative 2. And we need to understand all the details of this. Similarly, of course, if you divide 1 by 1/2, you get a positive 2. Now, another thing, this gives you information about the graph of the function. It gives you these 3 points and these 3 points. If you don't include the negative 1/2 and the 1/2, you just get 2 points here and 2 points here. You might think that you should just connect those points with a straight line. As far as you can tell, you don't see the curvature. Another thing is, and we explained this previously, you don't connect this point and this point. One reason you don't connect this point and this point is simply that this function is undefined when x equals 0, meaning it's undefined at every point of the y-axis. So if you try to connect from here to here, you're going to go across the y-axis and you're going to think that there's a point on the y-axis that's on the graph. That's not going to work. Basically, when you have an undefined, when the function is undefined for given value, what happens on this side isn't directly related to what happens on this side. Even though in this case there's a symmetry about the origin, and there's some obvious reasons for that, but we're not going to talk about that just yet. So, if you plot all of these points and understand, of course, that the graph is undefined at 0, you're going to get this much of the graph. Now, obviously, there's more to the graph than that, and I've actually extended the graph as it will extend. Let's see why it is the graph extends the way it does. Okay. Now, notice that 1/2 divides into 1 how many times? Well, you can count to 1 by 1/2. Here's a half, here's another half. There are 2 halves in 1. So that when you divide 1 by 1/2, you get 2. And of course, the calculation will give you that. If you do 1 divided by 1/2, you're going to get 1 times 2 over 1, which is 2. It's not the reason it's 2. The reason it's 2 is because it takes 2 of them to make 1. But that's how it's calculated, and that further justifies the reason. Okay, now if we cut 1/2 in half, we have 1/4, indicated by this somewhat smudged mark right here. And how many of those does it take to make 1? Well, 2 of them make a half, because of course we got this by cutting half in half. So it takes 2 of these to make a half, and 2 more to make 1. So if you divide 1 by this number, which is 1/4, whether you do it by inverting a fraction or whether you do it by just counting 4 of them in an interval of 1, you find that the result is 4. Now let's see, here's 1 and 2 on the y-axis. If we want to get 4, it's going to be up about here. So the graph will extend up to here. You could go further. You could cut that 1/4 in half. That would give you 1/8. But it's easy to see that it's going to take 2 of these to make a 4th, and 2 more to make a half. That's 4. And then 4 more to make 1. It's going to take 8 of these to make 1, so that 1 divided by this, the reciprocal, the 1 over x for this value of x, has to be 8. Well, that's 8. This is 4, so you're going to have 4 here and 4 more here. You're going to be up here someplace. If you go twice as close again, you're going to be twice that high. Twice as close again, you'll be twice that high. Every time you go twice as close to 0, you go twice as high here. And by the time you've done this 10 times, you're going to be 100 feet high. and I can barely jump that high. So, don't make me plot that point, okay? So the graph is going to go up very steeply. It's going to go up very high, and there's no limit to how high, because you can keep doubling the height, and pretty soon you're going to be out at the moon. Okay. But you're never, if you keep going twice as close to zero, you're never going to touch the y-axis. You're never going to hit zero. You're always going to be a little bit away from the y-axis, no matter how high you go. In that case, we call this an asymptote. We say that this graph is asymptotic to the y-axis, meaning it keeps getting closer and closer, but never touching. If we look at what happens when x gets big, well, we can kind of think in terms of doublings again. Here's 2. If we double that, we've got 4. Okay, well, if we double the value of x, it should be clear that 1 over x is going to become half as great. So every time we double the value of x, 1 over x becomes twice as great. So that when we go from here to here, well, the value of 1 over x is this. That would correspond to 1/2. And then we go out to here, our graph point is going to be twice as close to the x-axis because the value is going to be half as great. Then if we double that distance, it's going to be half as great again. So this point is some distance above the axis, half a unit above. The point out here will be twice that close to the x-axis, and the point out here will be twice that close. So we can see that we're going to approach the x-axis. We have to double our distance from the origin every time we want to get twice as close to the x-axis, but you can see that if we get twice as close to the x-axis just a few more times, our point is going to actually be inside the chalk line. Doesn't mean it's going to be on the x-axis. It's just I can't draw a perfectly, I can't draw a line. The line has no width. I can't actually draw a line with chalk. I'm laying down a layer of atoms here, or a layer of, mostly calcium. That's got to be in a compound. I don't know what the composition is. Anyhow, even though I'm inside my chalk line, doesn't mean I'm really at the middle of that chalk line, at the x-axis, and I never will be. So again, as we go out this way, the graph is going to become asymptotic to the x-axis. And a similar thing's going to happen on this side of the graph. Because, of course, there is a type of symmetry here. The numbers that we have going away from 0 here are the same as the numbers we have going away from 0 here, except they're negative, so that you can actually just kind of take this picture and flip it around, and you get this one.